So next, let's take a look at using the arrange function to rearrange the rows or observations in a table of data. So let's start by sorting MI flights from smallest to largest in terms of which day the flight took off out of. And then we'll print the first 4 columns and 5 rows. Okay. Let's make this a little bit bigger. There we go. Okay. So we pipe MI flights into the arrange function from dplyr. Okay, such that we sort by day, and then we will only keep the first 4 columns. And so we could do that by indexing the first 4 columns by using the numbers 1 through 4. You can also index the columns based on the names of the variables. So we can say the year variable through the dep time variable. So let's try that approach instead. Just like that. And then we want to print the first 5 rows of the resulting table, so we can use the slice head function, which prints the first n rows of a table of data. Here we go. And then we can even use one of our specialty functions for printing tables to make this look a little nicer. We can use the flex table function, for example. Okay. Just to make that resulting table look a little more tidied up. Okay. Now, let's see how we can also use the arrange function to sort from largest to smallest. Okay, by default, it goes smallest to largest, ascending order. We can modify the code from the previous part to easily change it. And to do this, we use the helper function BESC, just like this. And now it has the largest days to start rather than the smallest. Most of the time, the arrange function is useful when you want to display a table of data, and so you want those rows in a particular order. If you're not displaying any tables, then the arrange function usually isn't too helpful, because for most operations, nearly all things you do in R, the ordering of the rows is not too important. It's only when you're displaying an actual table. Arrange can also help us sort by multiple variables simultaneously. So for example, we can sort MI flights by the year, month, and day of the flight. Okay. And so note that this sorts in a particular order depending on how we specify the variables. So, for example, here we're sorting by year first, then month, and then the day of the flight. Okay, all ascending. So what this will do is it will take all the rows in MI flights that are in the earliest year, so 2019, and puts those at the top of the table. Then it puts all the rows for the next year, 2020, and then finally 2021 below all those. And then within each of those years, within each unique value of year, it sorts by the month. So then it will put the January flights first in each of the years, February flight second, and so on. And the day, it works similarly. Then within each combination of month and year, it will put the earliest days first. Okay, so day one of each month. So with this sequence of sorting based on these variables, the 2019 flights will always be before any 2020 flight. Okay. But if we had put day first, then all the flights on the first day of any month, regardless of year or month, would have been first, and so on. So the ordering of which in which you sort by variables does matter. Okay. And you just have to think about what you're hoping to get in your situation. So let's have you try this out yourself, some rearranging of rows here. So try out these three parts on your own. Keep in mind for the speed variable, or how we want to sort by speed, you'll have to think back to maybe your last physics class that you took using the distance and airtime variables to make your own speed variable. Okay, and note that you can use functions of variables inside a range. So try that out on your own and pause your video. And then once you've given it a go, unpause it and we'll look at it together. Okay, so let's try out these parts here now. All right. So we're going to sort MI flights based on the arrival delay to find the three most delayed flights and the three that left the earliest in terms of their separately. So two sort of separate queries here. Okay, so for number one here, we can say MI flights. We're going to arrange, okay, to find the three most delayed flights, we want sorting descending for the arrival delay. Okay, and then we can use slice head to get those top three values. Okay. We can see two of them were out of Grand Rapids. Yeah, they had some really big arrival delays. So these planes were super late. Well, it looks like they had pretty far destinations too. LaGuardia, Phoenix. I'm not sure what LAS is, but yeah, if you look at the distances here, you can see, right, yeah, very far flights here. But okay, so that was first part here, the three most delayed flights in terms of their arrival time, and then let's find the three that left the earliest in terms of their departure time. So for that, we want to sort by ascending departure delay. Okay. And we can see these planes left 54 minutes early, 49 minutes early, and 46 minutes early. Crazy early flights. Well, two of them out of Flint, and they were going to PIE, which is the St. Pete airport just outside of Tampa in Florida. For those not familiar, it's the smaller airport in Tampa. Flown in there once myself. It was nice. Uh, so some reason Flint to St. Pete is very fast. They're leaving very early sometimes. So next for number 2 here, the number 2 part of the U-Try, let's try to find the fastest planes in terms of their average speed for their trip. Okay. So we can take MI flights and we can arrange in descending order, okay, by speed. And so speed, if we remember back to physics class, distance divided by time. And our time variable here is given by air time. Okay. So if we do this, and then we can just print, say, the first 3 as well. These are the fastest 3 flights we've got. They were cruising. See, a couple of them left late, so not surprising. Maybe they were going a little bit fast. Although this one left right on time, and it was still cruising. All out of Detroit. Yeah, going various places. And this one even ended up early despite leaving late. This one was still late. Oh, all the same carrier though. That's interesting. This OO carrier. Not sure which one that stands for. Oh, SkyWest Airlines. Interesting. Apparently their flights go really fast sometimes. Okay. Maybe the same pilot who just really likes to push it. So next, finally, for this last part, let's look at just flights coming out of Grand Rapids. And among those, the 3 flights that traveled the furthest in terms of distance, and then within those, because we have a lot of flights going to the same places, so there's a lot of flights with the same exact distance, we want to find the furthest flights, and then those that arrived the earliest in the morning within those. Okay. So first, this is a multi-step problem here. We want to subset to only flights coming out of Grand Rapids. So let's use a filter. And so we can say we want to keep rows where origin is equal to GRR. Okay, this will then only keep flights that are coming out of Grand Rapids here. Okay, we can't see the origin variable, I guess, in the output, but we then, within those flights coming out of Grand Rapids, want to find flights that traveled the furthest distance. So let's arrange by descending distance. Okay. And then we also want to simultaneously sort by the arrival time, ascending, to get those that arrived the earliest in the morning. Okay, and then we'll get the top 3 earliest flights within those going this longest distance traveled. And so we can see for these flights, yeah, they all arrived early. Nice. For the furthest flights, it looks like the furthest flight that was flown out of Grand Rapids direct in these years was Grand Rapids to LAX, so Los Angeles. And then these 3 are the ones that arrived the earliest in the day in LA. Okay. So that's how we can use the arrange function to query specific rows that we're interested in or specific observations that meet certain criteria. So that can be helpful in some data scientist roles, right? You need to just, you don't always have to use modeling or machine learning methods to answer a question. Sometimes it's just as simple as subsetting to the right rows in the data table and sorting them appropriately. And often that can answer a lot of questions in itself that people are curious about. right? So I had a colleague at Minnesota who she used to work for Target as a data scientist, and all she would do very often is make different queries about tables that involved filtering, arranging the rows, selecting certain columns, okay, as we'll see here in just a second. So these can be important operations, although they're not the flashiest methods. They're still very important for data scientists. So next, let's look at the select function, which its name is inspired from a corresponding SQL function. So select allows you to subset columns of a table of data. In this case, we had columns or variables A, B, C, D, and we can subset to just keeping A and C. You can also use select to rearrange the columns as well, not necessarily just dropping them. And that's the main purpose of select. So let's demonstrate the select function's usefulness here by dropping the year and month columns from MI flights to create a new data set called MI dropped. So MI dropped. So we're going to use dplyr : select. Select is a very common function name, so it's best to make it explicit that we want the select function from the dplyr package. Otherwise, you can get errors that are a little bit hard to diagnose because your syntax could be correct for the select for the dplyr version of select, but it might be incorrect for other packages functions that they have called select, and they might not even do the same thing at all either. So I found it's best because this is not uncommon to cause an issue if you don't use this syntax. You can run into that, and it's very hard to diagnose that issue. So to drop columns with select, we can use a minus sign. So for example, here we can drop the year variable by using minus year and then minus month. And then we're creating this MI dropped table. Okay. And you can see in MI dropped, it has the same number of rows. So the rows were untouched, but now we have 35 columns or variables instead of 37. So those two, year and month, if you open up MI dropped, they're no longer in there. Okay, they were removed from the data table. Next, we will look at some of the more advanced options available when using the select function. So dropping columns can be helpful if you just have a handful, dropping them explicitly with the minus sign. If you just have a handful of variables to be dropped, this can be a useful thing to do if you have like a huge data set when you first open it up in RStudio and you really just want to subset things down, get things down to a smaller amount of data, because maybe you're only interested in a couple variables. You don't want all those other ones crowding things, making it a little bit slower to work with analyses. So dropping variables can be helpful for that reason, or just when you're displaying a table, rearranging columns can also be helpful in the same way that rearranging rows can be helpful, in that sometimes we want to show a particular result and it's important to us what order the variables are in, right? So some of the more advanced operations that we can do with select involve use of what are called helper functions that Hadley Wickham, the developer of the dplyr package, made. So the starts with helper function allows us to select any and all variables in a table of data that start with a particular string. Ends with works the same way, but if a variable name ends with a particular string, it will keep or drop those depending on what we specify. Contains is more arbitrary in that it's just if the substring is found anywhere in the variable name at all. And then the context of having variable names, for example, structured like var1, var2, var3 is so common that Hadley made a helper function called numRange that just gives the prefix or starting string of the variable name you want to match, and then you give the numeric indices for what you want to grab. Okay. These are the most commonly used helper functions, although there's even more with the select function. The other most common one that you would likely use is the everything helper function. This is particularly useful when you are wanting to rearrange columns in a table of data, but don't necessarily want to drop a lot of them. So for example, if we want to move the time, hour, and airtime variables to the front of MI flights, we can use this code here. And if you submit this to the console, okay, you can see how this still has all 37 variables, all 463,000 rows, but now this moved time, hour, and airtime to the front, to the leftmost side of this table. Okay, if we want to look at those. And as a reminder, this does not actually alter, this code here being run does not alter the MI flights table of data. If we open that up, we can see year and month are still the leftmost variables in the table of data. We have to overwrite MI flights with an assignment operator, okay, like this, the arrow. We would have to reassign MI flights to itself using this code if we wanted to actually alter permanently the ordering of the columns in the table. Okay. But here we were just showing how the select function can do that, even though this change was not permanent. So let's take a look at using these helper functions here. So another good point to go ahead and pause your video, try out these three parts on your own, see if you can get it without looking at the code that we'll write together. So hopefully you had some time to try that out. Now let's look at these three pieces together. Okay. So first, let's create a subset of MI flights, all time flights that only has the variables that end with the word time. So time flights, we're going to store in that the result of taking MI flights and then using the select function to keep flights that contain variables that end with the word time. So ends with time. And note that the string that we give inside ends with or starts with or contains is case sensitive. So variables in R have names that are case sensitive. So time is different than, all lowercase is different than time with a capital T. So here we can see for time flights that after dropping these variables, okay, we only have 5 variables left. And if we open that up, you can see they all end with time. So that can be a helpful way rather than looking through the table tediously figuring out which ones we wanted there. Okay, let's also do a similar operation. Departure info. But this time those starting with dep. So variables related to departure time. starts with instead of ends with. Okay. And if we look at departure info, we have two variables, departure time and departure delay. Okay. Lastly, we can make this table of data called new flights using mi flights. Such that we keep the flight number, origin, destination, moving those to the front of the table, and then keep all the other variables except tail num that we drop. So a little bit of a complicated operation here. Let's see how we can do. So we're going to call this new flights. We'll call it a complex rearranging and dropping of columns. So we are going to first, there's a few ways you could do this, and there's not one right way, but how I would do it is we want to put flight and origin at the front, those variables. So let's just do that to start. We want these at the leftmost side of the table, and then destination. Then we want every other column in the table, but we want to drop tail num. So this is one way you could do this. New flights now. Okay, flight, origin, dest are all at the front there. And there's no more, now this only has 36 variables. It dropped the tail num variable. Okay. So that was the select function. Now let's take a look at how we can use the mutate function to add new columns or modify existing columns in our table of data. So one variable that we could make is a new variable called gain that represents how many minutes a flight gained in terms of its arrival time mid-flight. And so we could calculate that by calculating how many minutes it was behind when it took off, and then how many minutes it was behind when it arrived. The idea being if it was 5 minutes late, so this would be 5 when it took off, and if it was 5 minutes late when they arrived, then their gain was 0 minutes. They didn't lose any, but they didn't gain any. But if they left 5 minutes late, so this is +5, and they arrived right on time, so the arrival delay was 0, then their gain would be 5 minutes. In other words, the pilot, they made up 5 minutes mid-flight by going faster, probably. Let's copy this code. Okay. Make a new section header here. There we go. All right. We can run that code. Oop. Oh, I broke the line. There we go. Okay. Now we can extend this code to use a single call to the mutate function to make a new variable called speed that involves the variable that we kind of implicitly used earlier in the arrange call. Okay. We're going to make a new data set called flight speeds. And it's going to have the gain, but it's also going to have the speed, which we said is distance divided by time. Okay. And then we can look at the top 5 rows here, but we can print that for the first time here, but we'll end up getting rid of that. Oh, yeah, actually, let's just get rid of that. That way we don't just store 5 rows and flight speeds. Okay. So flight speed should have 463,000 rows, 6 variables, about. And if we look at that, okay, we can see distance divided by time, 500 divided by 88. Gives you a speed of 5.68. So this looks kind of strange for the speed, right? So what went wrong here with our calculation of this speed variable? Why does it look so small? It's our units of measurement, right? So the distance is in miles, but airtime is given in minutes. So this is miles per minute. If we wanted to convert this to miles per hour, we can multiply by 60. That will give us the miles per hour. It looks much more reasonable for a flight speed, an average flight speed. Okay. Next, let's create a plot that shows the relationship between this calculated speed and the time the flight gained with an appropriate plot. So in this case, we have 2 quantitative variables, and we want to look at the relationship between the two. So we will use a scatter plot. Okay. So let's use our flight speeds data set. Type that into ggplot. Okay, and then we can think about what our x and our y variables are. So in general, with a scatter plot, you want to have x be your independent or explanatory variable, and y be your dependent or response variable. Here, talking about the speed of the flight and then how much time they gained, one makes more sense to be x than the other. So you want to think about which variable would affect the other one. In this case, it seems most reasonable to say that the speed of the flight is what affects the gain. Okay. And then we can add geom point to make it a scatter plot. Okay. Takes a little bit to run because we're plotting so many points. Okay, almost 500,000 data points it's plotting on the scatter plot. So R takes a second. But it's quite impressive that R can do it. Some languages just don't even plot that many points. They'll just do what's called thinning, where they randomly select some of the points to end up showing in the scatter plot. Okay, but R is actually plotting 500,000 points here. So now that it's done, you should be able to see this boomerang type shape in the plot. Okay, which is kind of interesting. When I initially made this, I expected to see a very linear relationship in that what I expected to see is that the faster the flight, the more time the flight would make up. That's what I was thinking I would see. In other words, a positive relationship is what I expected. Not the case at all, though, right? We have this boomerang, a more nonlinear, complex pattern going on, right? So I had to sit here and think about this for a bit, like, why is this happening? Um, so maybe keeping that in the back of our minds, let's add some plot labels. We can add a title, y-axis label, x-axis label, caption. Okay, we had our caption from earlier. Title, we could say something like Michigan flights 2019 to 2021. You can add a subtitle as well in the for the ggplot. So we could say exploring the relationship between speed and time gained. Something like that. Y can be like time gained. Oops. Time gained minutes. X is the speed. And remember, we made this in miles per hour now. Okay, so there's our plot labels. Oh yeah, it takes a little bit to run. Okay. I'll let it finish running this time. Whenever R is running something, as a reminder, you can kill the process by clicking this stop sign, but it won't give you the plot if you do that. But if you want to just move on because something's taking too long, you can always kill the process by clicking on the stop sign, or you can click on this red triangle as well to stop it running. Okay. There we are. All right, so it finished finally. Yeah, what we'll do, because we're going to keep tweaking this a little bit. Pro tip, when I'm working with a really big data set like this, I want the final visualization still, but to make my life easier in the process where I'm like updating small aspects about it, I'll do what I mentioned the other software does, randomly select just say 10% of the data points and make the plot so that it takes, it runs 10 times faster. And I'll just do that until I get to the very final version of the plot in which I plot the whole data set, okay, and let it take a long time on that final run. But in the intermediate steps, what we can do is use what's called the slice sample function. And that allows you to, let's see, I'll look at the help file. Slice sample function allows you to randomly select rows from a table of data. And you can use this prop argument to say, I want, for example, 10% of the values. Okay, now I can plot it. It'll look pretty much the same because it randomly selects those, but now it'll run about 10 times as fast. Okay, there we go. And so we'll do this until we get the plot finalized all the way. Okay. Plot's looking pretty good. So when there are this many observations, even when I subset to 10% of the values being there, you still get this opaque area in the middle of the cluster of points where you can't really see the finer aspects of the distribution. So one solution is to toggle the transparency of the points to allow the finer aspects about the distribution to be better visualized. Okay. So we can do that using the alpha aesthetic. We can set the alpha aesthetic to a smaller positive number. In this case, I played around with it, and I found that 0.1 for the alpha parameter helped out quite a bit in terms of displaying the scatter plot here. Okay. That allows us to see a little bit more nuance in the distribution of the points. Okay. We can also add a complete theme to this plot. So let's do that. Again, my favorite theme is theme few, but whatever theme floats your boat works great. Okay, so we add that theme. All right, perfect. Now, going back to what I mentioned earlier, if a flight is going faster, we in general should expect that it will arrive faster as well. In other words, its amount of time gained should be larger. But we don't see this clear positive relationship going on here. There is some noise, and it's not even still a general straight line pattern that's positive. So what's going on? So if we think about these flights a little more in depth, we saw before how some had flights going, say, from Grand Rapids to LAX to Los Angeles. That's a super long flight. While some other flights go from just Grand Rapids to Lansing. That's a very short flight, okay? How fast a plane is going is important in terms of its gain, but so is how long the flight is. If a flight is super long, Grand Rapids to LA, and it's going super fast, it will make up a lot of time. But if a flight is super short, the amount of time gained will be closer to zero probably regardless, because the flight being short doesn't allow for the speed to matter much in terms of how much time is gained. Okay. So in other words, there's an additional variable interplaying in the relationship between speed and time gained, and that's the distance of the flight. So in general, I would stick to 2 or 3 variables in a single visualization at most. You want to shy away from using too many variables, but ggplot does allow us to include additional variables in the plot. For a scatter plot, we can include an additional quantitative variable by mapping to the color aesthetic. So if we say color equals the distance of a flight, okay, what that will do is ggplot recognizes distance as a quantitative variable, so it'll create a color gradient. In this case, it's having darker points be shorter flights, and then lighter colored points be longer flights. And we can move the legend here to the bottom of the plot. So let's add a theme layer. Okay, move the legend to the bottom. Now with the legend at the bottom, that gives the scatter plot a little more room to stretch out. We can also alter this legend title here to say distance in miles. Okay, so the color aesthetic is what generated the legend. So we use color in the labs function to specify to customize the legend title. Okay. All right. And then, yeah, this looks like our final plot. So let's get rid of that slice sample portion that reduced the size of the data. Okay. And then what we'll do is we'll also use this argument, this code chunk argument, cache equals true. Okay. And so what this will do is when you have a code chunk that you have finalized and you are no longer going to alter any further, you can cache or store the result of what this code produces by using cache equals true. And R will save this as an additional separate file on your computer, and then just read in that result instead of having to rerun this code every time. So when we knit it now, it'll have to run this one more time, and it'll save the result of this plot. And then with subsequent times that we compile our document, it will no longer have to recompile this code. It will just read in that image, for example, in this case, and just include that. Okay. So this can be helpful if you have code that takes a really long time to run. Using this cache equals true argument allows you to run it once quite slowly and then save your result for future compilations of your document. That only works again if your code is not going to be altered any further in this code chunk. Otherwise, that will cause you issues. Okay. Sometimes R just recognizes you changed things and then we'll recompile everything again, but it sometimes might not, and then you would end up with code that doesn't match the actual output. So you have to be careful of that. Although most of the time R should recognize that you altered the code. So here it's taking a little bit longer to run for that final time, but it's going to save that file and it'll save us time for the rest of the activity. Maybe while we let that finish running, let's take a look. Okay, that was the last part for the mutate function. So we can add a new section down here while that's finishing up to start on group by and summarize. Ah, there we go. It's finishing up here. Okay, so if we look at our final scatter plot, there it is in all its beauty. Okay. So for this final scatter plot, we have that the shorter flights that have darker points. Okay, notice that there's not an apparent relationship between time gained and the speed of the flight. But if you look at just the lighter colored points, there's this positive relationship between how fast a plane is going and the amount of time it gained. So an important multivariate setting going on here where we have multiple variables interplaying with one another. Notice that the legend here has some spacing issues in terms of the numbers overlapping a little bit. In this case, since I did run this and now I do want to change something actually about it, but we cached it. Okay, to show how you would make sure there's no issues with that real quick. Let's look back at R. When you look back at R, you can right click next to knit, this little triangle, and there's a clear knit R cache button. So just to make sure there's no issues, I'm going to click that, click yes, essentially get rid of any previously stored code chunk cache. Okay. And then we can add in, if you add in this layer to the ggplot, scale color gradient. Okay, this allows you to specify the breaks in the legend so that they won't overlap. And then we can also format them to have a comma since they're over 1,000. So if we rerun this, it'll take a little bit to run. And it's going to take a little bit. It's trying to save it again, rerunning this scatter plot. Yeah, the scatter plot again takes so long because it's almost 500,000 points, but this should be the last thing that we have to update about the plot. So caching it should save us time here. There we go, nearly done. And if we look at that result, there you can see that the legend now does not have overlapping labels and even has commas formatted with it. Okay. So overall, the pattern that we see is that there's a positive relationship for longer flights between speed and time gained, but for shorter flights, there's not much of an apparent relationship present. Next, let's look at how we can calculate group-wise summary statistics using the group, by, and summarize functions from the dplyr package. So this allows us to take our table of data, consider subgroups of it, and calculate summary statistics for each of those subgroups. Okay. In this case, it was, for example, calculating the mean of the variable b for each level or unique value of a in the data set. Okay. So one thing we can do, for example, is get the average departure delay by day of the year, and then just print the first 5 rows of that. So there were several flights that went out each day, and then here's the average delay in minutes for each of those days. Okay. A lot of rows in this. That's because we grouped by year, month, and day. If we added a ungroup option here, the group by, when you apply a group by to a table of data, it's kind of sticky is one way to think about it. It will hang around, and if you try to do subsequent functions, if you try to apply subsequent functions to the result of something that involved a group by, it will still apply those functions for each group-wise combination of some of these groups. Okay, and so you end up with, in this case, it was printing 5 rows for each of these different combinations of month and day. But if we use this ungroup function, it can peel back or undo the group by that was applied. And then we end up with only 5 rows like we actually were asking for. So in this case, we were calculating average departure delay by date. Okay, the combination of year, month, and day determine the date of the flight. So that's how to calculate an average departure delay by date. Next, let's work towards reproducing this plot below, which some people call a waterfall chart. And this shows the average delay in minutes for each of these different major airline carriers, okay, in this data set. Okay, and sorted by the size of their average delay. So we can calculate the average delay using this code here. So we group by carrier, and we calculate using the summarize function the average delay, arrival delay. Oh, arrival, not departure. So summarize behaves very similarly to mutate, except summarize will typically reduce the number of rows in your data set because it's calculating a summary metric for each specified subgroup. Okay, whereas mutate does not reduce the number of rows. It will just calculate a new column, and there will be the same number of rows as you had before you applied a mutate. So to make this waterfall chart, this is essentially going to be a bar chart or a bar plot. And so we can calculate that or create this bar chart by using ggplot here. With these calculated delay summaries. So if we look at this condensed table now, gotta run it first. What we see is that now this only has 16 rows and 2 columns. Carrier name and the delay, the average delay in minutes. So we really condensed down almost 500,000 rows into just 16. we're going to use this table to make the bar plot. Okay. And so we're going to do that by using the geom call function. We're going to pipe the delay summary into ggplot. X specifies our horizontal axis variable. In this case, we want that to be carrier name. Y is going to specify our vertical axis variable, which we want to be the delay, average delay in minutes. So Y is delay, X is carrier name. And then we want to make a bar plot. So we're going to use geom call. And that will give us a bar chart to start, bar plot. But we want to sort by the height of the bar. Okay. And so one way we can do that is using the reorder function. So around carrier name, we're going to say reorder carrier name and then by delay. Okay, and if we do this, we can see the bars are now sorted in ascending order, just like in the activities visualization that it's showing. We can update the plot labels. Okay, so we've got the average, it's actually the average delay in minutes. And it's, if we want to be specific, the average arrival delay. X in this case is the carrier. Yeah, we can just, maybe we can say arrival delay in minutes, and we can say, in the title, we can say average arrival delay by carrier. Okay, and then we can add in a caption if we wanted to, just like we did before. Okay, we got our nice plot labels there now. So now it looks pretty good, right? We could just call it a day here. Now we want to fix this up, right? So one thing that ggplot does that's not ideal, if you have a bunch of these labels on the x-axis, it just throws them all on top of each other and sends it off to you like, there you go, there's your final product. But of course, we want to fix this up, right? This is not legible currently. So there's a few ways we can do that. So one way that we can fix the issue with the plot labels here that are overlapping is to use a theme layer, specifying the argument axis.text.x equals element underscore text. So the x-axis text is a text element of the ggplot, and so we can customize it accordingly using element underscore text, which has lots of different options for customization, including color, font family, horizontal adjustment with HJust, vertical adjustment with VJust. We're going to angle the text, saying we want it to follow a 45-degree angle. We want to then adjust the size of this font a little bit. Have a horizontal adjustment of 1 and a vertical adjustment of, in this case, 1. Okay, I had to play around with these values a little bit. And that ends up making these plot labels a lot more legible here, and so that they don't overlap each other. Okay, we can see that if we knit the document here now. Okay, and let's look back at the activity while we knit that. Okay, we're nearly there. We just want to bold the titles and add a complete theme to the plot. Okay. So in this case, okay, here's where our plot currently stands. Nice, it's looking good. You'll notice, yeah, this airline has this little bit of weird thing at the end of its name. It's cut off in the activity, but not sure why that was showing up in the carrier name here now, but it seems like a miscoding in the data, a little bit of a data error entry, but we can next apply a complete theme to this and make sure we bold the title text here. So to apply a complete theme, we'll do that before the final theme layer. To match what I used in the activity, I used a black and white theme. Okay. And then to bold the text, we can, in the theme layer, use the argument text equals element underscore text and say face equals bold. That bolds all the text elements in the plot, makes it a little more readable. Okay. And then the last thing that we're going to do is we want to match the color scheme used here such that we have these reddish bars when the delay was negative and blue when it was positive, right? So these are colorblind friendly versions of red and blue. So we can't just specify the color red and the color blue, or else it won't look quite like this and it won't be colorblind friendly necessarily. So we can use what are called hex codes for these colors. Hex codes are unique IDs such that you can get a very specific color and have it match uniformly across different software applications, different programming languages. So in this case, this is like a unique identifier or the hex code for this specific red. And this is the unique hex code or identifier for this specific blue. And then if you used a different programming language, even like Python, or if you used Microsoft Excel, for example, to make a plot, you could get this same exact blue and red with these colors. So that can help you match colors, say for a company logo or something, if you wanted to have a consistent theme or styling to your plots. For example, you could get the Grand Valley blue. You can look up what the hex code is by Googling that and see what the unique ID is for the exact blue for Grand Valley's logo. So kind of fun. And in this case, it helps us to use colorblind friendly colors since I looked these up and made sure they're colorblind friendly. So to get those colors in the plot, we're going to use we're going to specify the fill aesthetic inside AES. And here we're going to make a variable sort of on the fly. We could use mutate to make a variable for whether the delay was negative or not, or we can just say delay being greater than 0 right here. This implicitly makes a variable underneath that will be mapped to the fill aesthetic. Okay, Hadley actually wrote the code that it will use mutate underneath here to make a variable equal to the binary indicator of delay being greater than 0 or not. Makes this visualization here. Uses the default ggplot colors, but we'll suppress this legend here. We can do that in the theme layer. Doesn't really provide us with much information. We can already see if it's negative or positive from the plot. Okay. And then the default colors from ggplot are not great. They're not colorblind friendly. So we're going to override that using these hex code colors. And in this case, we can use scale fill manual to do this. Okay. And RStudio colors these because it recognizes them as colors. In newer versions of RStudio, it does that. Okay, and beautiful. There is our wonderful looking waterfall chart. So let's let that knit while we look at the next part of the activity here. So for the next part, go ahead and try these next few parts on your own, looking at the median flight delay instead, based on the arrival delay by month, to visualize which months are the worst in terms of delays and which ones are the most earlier on time. Okay. And note that for the median, it might not be that you might not have negative values anymore. Okay, so that don't be surprised by that. So go ahead and pause your video, try these parts out on your own, and then we'll look at it together. So hopefully you had time to try it. And then let's take a look here. Okay. So to summarize the median flight delay by month, okay, we can use very similar code. So let's copy this first code chunk. Okay, and then we're going to get the median arrival delay for the different months. Okay, so we can say, maybe we'll call this like month delay summary. And then we can group by month now instead. And we'll say delay equals median delay. Okay. Then we can copy the same code for the bar chart. That's going to be nearly the same. So we get month delay summary. And now instead of carrier name, we want month. We look at this data set after we run it, month delay summary. We open that up. And then we have the day, the month of the year, and then the median delay. Okay. And then, oh, actually, we have all negative values. None are positive because the flights were always on time in terms of the median, at least. So looking at this, there's a few options for how you could handle this. Oh, let's update our plot labels too. So arrival delay. So we say median. Arrival by month. And maybe instead of delay, since the medians were all early, we can call it median arrival time by month. And then we'll say like minutes early. Okay. So we look at this. It's upside down. We can flip that. We could calculate the negative of this if we want to show the minutes early like this. So we can say y equals negative delay. Just like that. And notice by default, it sorts, or not by default, here it's sorting based on the height of the bars, which we wanted for the carrier, but month is an ordinal categorical variable, so we want to just keep it in terms of the regular ordering, 1, 2, 3, 4, 5. So we will get rid of this reorder part and just call it month. Fix that part up. And there's a lot of choice here. There wasn't one way to do this plot, but this is one way we're choosing to do it. Okay. Next thing, let's see. The text is angled, so we no longer want to angle it because it's not necessary. Let's get rid of this axis.text.x part in the theme. Yeah, that's no longer needed. Plot labels are not overlapping anymore. Perfect. Oh, it says carrier. Let's call that month. All right. Perfect. Now we're nearly there. We have some extra space below 0 in the x-axis. We can fix that up using a scale y continuous layer with that expand equals expansion argument. Earth. There we go. And then we can look at customizing the x-axis to have not decimals in the breaks, right? We don't want that. Using a scale x continuous layer, we can specify the breaks to manually be the numbers 1 through 12 by creating a vector of the numbers 1 through 12 here. Okay. Perfect. And then these bars, they don't need to be this strange red, right? We could just do whatever color you'd like. Dodger blue is one of my favorites. So there we go. Here's a visualization of the median flight delay, median arrival time delay in terms of how many minutes early. So we can see flights in January in Michigan tend to arrive the earliest in terms of the median. The worst delays, or the least early, I should say, is the month of June. And there's definitely a temporal trend, a trend across time where it looks like the summer months, planes struggle to be early in Michigan, and the winter months, surprisingly, even though the weather is maybe not as nice, looks like they arrive earlier. Maybe because they account for possible delays due to weather, and so they leave earlier. I'm not sure. But yeah, we can definitely see that trend here. So we can also use a line chart here. So this bar plot is one way to visualize this data, and it's certainly valid, but we can also use a line chart to show more of the trend in these points. And so if we take this code, since the x-axis is a measure of time in a way, the month, and the y-axis is a quantitative variable, a line chart is a natural visualization for this type of data. So we can do that using geom line. Oh, we get rid of this, yeah, this fill. Actually could have done that in the previous code as well. The fill aesthetic is no longer doing anything here, which means we can get rid of the legend.position equals none. Wasn't hurting anything, but it just wasn't doing anything in the code. Okay, so for geom line, we have the month, the negative of the delay, which in other words gives us how many minutes they were early. Okay, and then here we see this trend. And with the line chart, we do want to expand a little bit below the lowest point in the chart. So we can just get rid of this scale Y continuous layer for the line chart. So removing the scale fill manual layer also because it was unnecessary, and using a line chart here. This was a good overall visualization for seeing this temporal trend in the median arrival delay, or how early the flights were across time. We can extend this plot a little bit further by faceting based on where the flight departed from. Okay, using group by. And so we can do this by modifying or extending this code from before. A line chart. Okay, where we group by origin as well. We add that as an additional grouping variable. And now we'll take this code, the line chart we just made. Okay, change the data set name. And then we'll add a facet underscore grid layer where we can have origin be the, let's say, the rows. Let's try out how that looks. Oops. Create the data set by running this code chunk, and then let's see. Unexpected. Oh, maybe I need a decimal there. Yes. There we go. Okay. And that gives us a different line chart for each major airport here. Okay, it looks like we have this general trend of June, July tend to be the least early across all the airports, which is kind of interesting. So certainly seems like a temporal trend. And then, yeah, March and April seem like they have some of the highest rates of being early, or the most early in terms of the median, which is interesting as well. Okay. So the final thing we'll look at in this activity is missing values. Missing values are really a thorn in your side as a data scientist, but it's important to not just brush them under the rug and sort of directly head-on address them. It's a unenjoyable step. It's not the most enjoyable thing to do, but it's best to just be clear about how you handle missing values and transparent in your assumptions and limitations that result from your handling of missing values. So a couple packages in R that really make our lives a little bit easier when working with these missing values are the mice package, which stands for multiple imputation via chained equations. I believe that's what mice stands for, and the nannyr package. Okay, the nannyr package was created by a couple people, one of whom was Dr. Diane Cook, who was Hadley Wickham's advisor in grad school when he was a PhD student. So Hadley's the creator of ggplot2, one of the lead developers of the tidyverse. His advisor is one of the people who helped make nannyr. So it's a really great package that plays very nicely with ggplot2 for visualizing missingness. Okay, like this first visualization we'll make here was made with nannyr. The mice package is really useful for imputing missing values. So in other words, patching or filling in missing values with our best guess of what that value should have been using lots of different methods. Okay. So we'll mostly focus on the nannyr package here, but I also just wanted to bring attention to mice because it's by far the best package for imputing missing values in your data. So first, let's just create a simple lollipop chart, which is a chart with a circle at the end showing what percent of values we're missing for each of these variables. Okay. And one of the great things about the nannyr package is the conciseness of its code that is required to make a lot of these plots. So for example, for the ggmissvar function to make this lollipop chart, all we have to do is make sure nannyr is loaded, which we actually already loaded at the top of our activity. And then we can use the ggmiss var function around our data set. Okay. It defaults to counts for a number of missing values. Okay, and it's giving them in scientific notation here. In my opinion, it's nearly always the case that the percent of missing values is more important, arguably more important, although you can always look at both. But to get the percent of missing values, you just add this argument, show underscore PCT equals true. And now we have a very quick, concise set of code that gives us a nice overview visually of the percent of missingness for each variable. So this makes it very clear. Skim, as a reminder, gave us, if we knit this document, let's take a look and compare and contrast what Skim gave us versus the ggmissvar function here. Okay. Just taking a little bit to knit, but there we go. And so if we look at the output from Skim from the top of the activity, okay, Skim does tell us the number of missing values, although it's in this table. So we have to look at the numbers and kind of visually compare that. We have the completion rate, so we can compare that as well. But still, a table of numbers, just naturally for us humans, it's a little bit harder to process that information all at once compared to a visual, right? Visuals just, we, again, just as humans, understand so much more quickly, so much more efficiently. So this allows us to very quickly see, okay, yep, precipitation, temperature, dew point, humidity, pressure have lots of missingness, nearly 100% missing. And most of the other variables are much closer to 0% missing. So in like a timed data science interview where you're strapped for time, this is a great way to quickly acquaint yourself with your data set in addition to Skim, using the Skim function, so that you could see, oh, these variables have way too much missingness to do anything meaningful with. I'm just going to make note and show this visual to say, hey, seems like a lot of these values were missing. It's something we would need to dig into further, right? But the rest of the variables seem good to go, although there's a little bit of missingness for a lot of the weather variables as well still, okay, but not too bad. So the ggmissvar function is great. You can also facet to where you can look at patterns of missingness stratified by a categorical variable of interest. In this case, we can do it by the origin of the flight. And again, the conciseness of the code is absolutely wonderful because in my years of working in R, I have yet to see something that visualizes missing values this nicely. Okay. So we can save. We can get this by copying the code from before and then adding a argument to say facet equals origin. Okay. And if we run that, you do have this issue of the plot labels are overlapping a little bit. Okay, if we knit the document, I believe it's still an issue, unfortunately. Okay, but let's take a look at it. And so we'll talk about how we can work around this, because this can kind of be a common challenge that one encounters when working with ggplot, is that the font size doesn't always scale very well when making complex visualizations. Okay, yeah, here you can see, even in the finished knitted document, the labels are overlapping for the variable names, not ideal, right? So there's a few ways you could fix this. How I tend to do this is by storing this ggplot in an object and then saving it where I can control the dimensions of this ggplot, okay, more explicitly. So example, we can store this in some object. Maybe we'll call it faceted lollipop. And then we can save it using the ggsave function. And so ggsave allows you to save a ggplot object you've stored. You need to specify the file name. In this case, we'll just say like faceted lollipop .png, something like that. And it will have some default width and height parameters. We're going to customize those. I had to play around with this to get something that looked good for the activity. So that's how I know what these values should be. I'm going to create a scaling constant, scaling factor, essentially called scale number. And we're going to use that to specify the width and height. So the width will be 1938. Again, I had to play around with this a lot to get this. Height equals 1700 times this scale number. And then the units, you can specify inches, centimeters, pixels. In this case, we're going to say pixels. Units equals px. Okay. And then what I also did when I made this to make it look nicer for the activity, I added onto the faceted lollipop a theme layer such that I modified the font size slightly for the y-axis text. Not sure if this is entirely necessary, but this is how I ended up getting the plot for the activity such that it looked nice. Okay. And I bolded font as well. Okay. So we can run this. It creates this plot, and you can actually open up the PNG file that's created. If you look in your files pane, okay, you have to navigate to where this activity is at that you have saved. You can hover over your R Markdown file name. Okay, I see, for example, in mine, it's a little bit small, but I see my current R Markdown file is saved in my completed activities folder. And so that happens to be right here as it is. You might need to navigate to it, but I can sort by modified. Okay, you can click on the PNG image and then you can check it out. Here it's a little bit dark, so it's a little bit hard to see. But once we include it in the HTML document, it will look better. And so we can include that. One way to do that, use the markdown syntax that we learned in our markdown activity and say faceted underscore lollipop. In our markdown or Porto activity, and then use the same file name here. Let's see. Oh, no, I'm sorry. That's the wrong syntax. We're going to use it like this. And then say width in curly brackets equals 700. Okay. I got rid of any spaces inside here. Okay. Now if we knit the document, you can see this should look better in terms of the scaling of the axes and the text overlapping or not. This should make it such that the text is no longer overlapping in the y-axis. Okay. And if we look at that result, we can see that that's the case. So a little bit of a pain to play around with the relative size of the plot to get it to not overlap, but overall we end up with this nice, beautiful plot here. And so we see some interesting patterns or trends in the missingness here. We can't necessarily assume that just because these variables had the most missingness overall in the data set, that doesn't necessarily hold the same for every subgroup in the data. And in fact, we see there's some differences in patterns here. Flint has a lot more missing values for these variables than the rest of the data set. Okay, and these are variables that all describe the machines that the flights are operating on themselves, the planes, the type of plane, the number of seats it has, its model. For some reason, Flint has a lot of those variables values being missing. And then Grand Rapids tends to have a higher rate of missingness on those plane variables as well, which is interesting. It also looks like in terms of missingness for arrival times and arrival delays, Grand Rapids tends to have, it looks like some more missing values than other places, at least at a higher rate. Maybe similar to Lansing and Flint, but Detroit definitely looks like it has the lowest rates of missingness among the airports, which is interesting. So this ggmisvar function allows us to see differential patterns in missingness here, which is nice. Another way we can visualize missingness in a similar light to this is to use the ggmiss factor function, which creates a mosaic plot. Mosaic plot conveys similar information, but does it in a different way. So this is using coloring rather than a lollipop chart to signify how much missingness there is in different variables. Okay. So to reproduce this mosaic plot, we're going to use this ggmiss factor function. Okay, so we're going to say mi flights. We're going to subset the variables because there's only some we're going to be interested in here. Okay, we're only going to select the origin, destination, carrier, and then variables that contain the strings time, or delay. And then we're going to pipe this right into the ggmiss factor function, where we'll specify the factor variable that we want to visualize the missingness for. Okay. And this gives us the same visualization, that's the same mosaic plot that's in the activity. This shows us how, for example, yellow having the most missingness, Grand Rapids has the most missingness in the arrival and airtime delays for some reason, with Flint and Lansing following close behind and Detroit having the least amount of missingness. Okay. And it looks like the same goes for departure times and departure delays. So there's some strange thing going on about Grand Rapids Airport over that time span, such that a lot of their departure times and arrival times and delays are missing at a higher rate, at least, than the other airports. Although, notably, the rate of missingness is still less than 5%, even for Grand Rapids. Okay. In some contexts, that might be a lot. In others, maybe it's not so bad. I'm not sure about for airports, to be honest. So, okay. So looking at even more complicated visualizations for missingness, we can look at the cross section of missingness because, again, as from skim, just because pressure is missing, say 90% of the time, humidity is missing about 90% of the time, we don't know the pairwise completeness of variables. Like, is every observation that has a missing pressure, does that also have a missing humidity level? it could be that the non-missing values are not overlapping with each other. Okay, or similarly, are the plane metrics missing jointly, or are they sort of separate from each other in terms of when they're missing or not? Okay, we can't know that for sure just looking at this visualization. So we have to look at the cross section of missingness across variables, which is a lot of different interactions. But this ggmiss upset function can help us visualize some of the interactions in terms of missingness, the cross section in missingness. So let's just isolate the weather variables here, some of those, and we're going to look at this plot. Okay. To make this visualization, we're just going to focus on some of the variables related to weather. Okay, so we're going to take MIFlights, type that into the select function, and we're just going to select temperature through humidity, and then precip through pressure. Okay, just because that's what we're doing here. If you focus on too many variables, this plot can get hard to read, and it subsets automatically using ggmiss upset to only a few variables with the most missingness. So, okay, this gives us this cross section of these variables here. So what this plot is telling us from ggmiss upset is that there were 430,000 roughly observations that had all 5 of these variables have a missing value at the same time in the same row. There were about 11,000 rows such that the flight was missing everything here except precipitation. It was missing temperature, dew point, humidity, and pressure. Okay, but then it had a precipitation, but none of the other values. Okay, and then this one just had a missing pressure. Okay, but the other variables were non-missing. This one just a missing humidity. Okay, so there's some kind of complicated interactions of missingness. Although the main takeaway here is certainly that when one of these weather variables is missing, it's very likely that the other weather variables are missing as well. Okay, the vast majority of the time. Notice that this uses scientific notation. There's not an easy way that I've found, at least, to override this behavior by default. So this isn't the most professional looking visualization because of the scientific notation, but it's still extremely useful and certainly something to consider when exploring a data set for the first time. So very thankful for the creators of this package. They did a wonderful job in making it here. All right. So as a last part for you to try, let's pause the video and give you a second here to try to visualize the missingness for each variable depending on carrier. Okay, and you might need to use a select to pick out certain variables to subset to here. And then also try and make this visualization with ggmiss upset, where again, you'll have to try out using select to subset to some variables to start. So I'll give you a moment to try that. Now let's try that on our own. Or now let's try that together, I should say. So to visualize the missingness for each variable depending on the carrier, what we can do is type into the select function. And we are going to select origin, dest, carrier name, and then the variables that contain time or delay. And then we're going to pipe the result of this into ggmiss factor. Where we say the factor is the carrier name. There we go. So here we can see that this ExpressJet Airlines, they had the highest rate of missingness in terms of the departure delays and arrival delays. Maybe if we were like a auditor and we wanted to see who's actually reporting their delays and who's not, this would be a good way to explore it by some grouping variable. We can see like Endeavor Air is doing a great job. Spirit Airlines, hey, look at all the flack that they get on late night TV. But look at them. They are reporting when they have delays and when they're not. They're doing a wonderful job, right? Allegiant, not as much, right? They got some room to improve here. They got some missing values in this data. Let's see. So next, yeah, this is like the U try. That was the first U try. Next, we can visualize the joint missingness of variables using ggmiss upset here for these departure and arrival times and delays. Okay. So we'll use similar code to before. Let's take the ggmiss upset code from before. We're just going to tweak it. So here we're going to select departure time through arrival delay. And then we can specify how many sets of variables we want to compare, how many variables we want in these joint-wise comparisons. I found that this argument doesn't always work perfectly in terms of like if you specify it too large, it doesn't always listen. Sometimes it'll just give you a smaller number of variables, even though maybe you asked for more. But you just got to play around with it. And even though it's not perfect, it still does a really good job. And again, there's nothing that comes even close to doing this good a job for visualizing missingness in R. So it's a wonderful package and lucky to have it. So here, for example, we can see that, again, similar to the weather variables, when one of these delay variables is missing, it's very often the case that the other variables are missing as well. Okay. Although arrival delay tends to be like the most missing just on its own, while all the other values are there, which is interesting. Especially since when you have the scheduled arrival time and you have the actual arrival time, you can calculate the arrival delay. So 915 of these we could patch in ourselves since there's a one-to-one relationship between what the arrival time actually was, what it was scheduled to be, and the delay. So this could be filled in. These should not be missing. But like this one's understandable because if the arrival time is missing, we don't know what the actual arrival delay was. And same with the last bar here. Okay. So that was the last thing for the U try. Let's knit the document one more time. And while that's knitting, just talking about missing values a little bit more, some high-level pieces of advice for common pitfalls for those handling missing values for data scientists. We want to avoid what's called complete case analyses. So a complete case analysis is where you simply drop, say using filter or other means, any rows that have missingness. For example, you can do this using the drop NA function, but don't do this, it's bad to do. And there's certain methods or functions in R that can not work if you have missingness, if you have missing values. And so this can be a tempting solution since it's so easy to implement, right? Just drop all the rows that have missingness. But you very much bias your results by doing this, okay? So instead of just dropping rows, you should, especially if you have a larger amount of missingness in your data, you should use imputation, okay, to handle those missing values. Okay, so imputation is generally the process of replacing missing values with our prediction of what that should be, what that value should have been. And so there's many different imputation methods. Some are much better than others. Some of the most commonly used imputation methods are what's called mean imputation or median imputation for quantitative variables, where, for example, if the departure delay is missing for a row, just fill in what the average departure delay was for the whole data set and just plug that in here. Okay, that's an approach people use. That's called mean imputation, or slight variations of that. You can also use the median for the whole data set, or the mode, which is the most frequently occurring value for categorical variables. That's how you can patch in, say, if origin was missing for a flight, you could just patch in what's the most common origin for flights in this data set. These mode or mean imputation methods are not good to do in general. They very much bias your data. They artificially reduce the variability in your data, because you can think of, like, in an extreme case where half of your values are missing and the other half are not. If you do mean imputation, you'll end up with half your data set has a constant value that's exactly the same. So some people like it because it preserves what the overall mean of the data set is, but even though you've preserved the mean, you've drastically altered the variance or variability in your data set, which is not good. That can affect modeling outcomes. And the other reason it's poor is that there's not necessarily a reason to assume that the mean is what the most likely value is for that missing value, right? So again, just because the average delay was maybe 10 minutes for this whole flights data set, that does not mean it's a reasonable assumption to plug in 10 for every missing value here. Okay. It could be that systematically the missing values are for flights that were so chaotic that maybe their delays were actually far worse than the rest of the data. Or maybe on the other hand, they were flights where everything went extremely smoothly and systematically for some reason. And so those just didn't have delays recorded. We can't know for sure either way, but assuming that the mean is a reasonable substitute for the missing value is not a good approach in general. Okay, so we want to use more sophisticated imputation methods that use predictive modeling, or variations of that, to patch in these missing values when possible. Okay, for time series data, another common approach for imputation is to just carry the last observed value forward. This is not as bad as mean imputation, although it has a lot of limitations itself as well. As I mentioned, predictive modeling is the best approach, which is what the mice package can be used for here. However, even when using predictive modeling, it often requires relying on strong assumptions about your data to patch in those missing values that many would argue are unrealistic in most situations, or many situations at least. However, reading into the different imputation methods that are available, like in the mice package, you can be transparent about the limitations in your approach for analyzing your data. The key thing is to be transparent about what you did. Don't just brush it under the rug. Don't patch the missing values and never mention it. You want to be clear about what you did for reproducibility and transparency in your analyses. Okay. Always good to list out your limitations yourself rather than let someone else point them out. Okay, that looks much worse if someone else is pointing it out and you were trying to brush it under the rug. Just be upfront about what you did and potential limitations with that. Okay. So the last thing, we have this optional bonus part in the activity. So you can go ahead and try that if you'd like, but it's entirely optional. Okay. Otherwise, that's it for this activity where we looked at data manipulation and data transformations with the dplyr package.